what are we talking about, right? So we spent some time about a few minutes ago discussing this rewiring, right? This way to change the model to move it to something else. So now, can we do it even with model that is frozen, right? This is one really interesting question that people ask, which is to say that if I completely freeze the model, can I still do some new task that you never have specified very clearly? Then of course is the adaptation part, which we already talked about. How can I do with small number of parameters? How can I move the needle? Again, lot of things basically I am skipping. I am picking only a small subset of the literature and the field that has gone into these aspects. But let's start with this, one of these again landmark papers, which is titled Language Models Are Few Shot Learners, right? So what is a few shot learning? So the few shot learning is essentially something of this nature. Purely by examples, we as humans can come up with patterns of what is asked, right? So if I were to, of course I have given the answers here, which I probably should not have, but let us say you ask the question, Federer is to tennis and Kohli is to, right? So I just leave it there, and then most even a 6-year-old, 7-year-old would say it's cricket, right? So we did not tell that the relationship I am asking is the sport. You just gave one example of it. Now the mapping function got learned that the sport is what is relevant here. Same thing with the same inputs. Let us say Federer, instead of being tennis as the next argument, I give Switzerland as the argument. Now you start seeing that the model tries to map that the function it has to learn is the country of origin and not the sport that the person plays, right? I could have given Kohli too, then the model would have responded with the answer as India, right? So now this is basically in the modeling world called a few shot, in this case a one shot, right? You just give one example and the model kind of learned that, right, it has to worry only about the sport that is being played or about the country of origin. Now how does it happen, right? Or a more formal way of studying this. A formal way of studying this is to parse inputs as x1, y1, x2, y2 up to xn, yn, and then you leave it at n plus 1 sample. And then you ask the model to fill up that n plus 1 sample. So inherent to this is the model has to learn a mapping function, right? F of x. F is not defined. F is only given in the form of examples. x1, what is y1 connected to x1? What is y2 connected to x2? The model has to learn this and has to apply that function on the new sample xn plus 1 and give you the output, right? In addition to all this learning, we are saying we don't want the model to change its weights, right? So you are not letting the model to change its form or fashion, right? You are not learning a new set of weights to cater to mapping xn to yn. You are not having a loss function that drives the model's output for every x, the corresponding f of x. All you are saying it is the weights of the model being frozen, then the model has to essentially use some other way of storing the internal calculations needed to generate the output. So the internal representations of the model builds this mapping function. So in this case that I'll talk about, I'll move this, right? So whatever x1 is to y1, x2 is to y2 and so forth, you keep providing these samples, right? Then you ask the question at an n plus 1 stage. So people have started analyzing how it does this, at least for problems which are simple, and come up with, let us say, ways to highlight that in simple cases it is the hidden representations, the rich hidden representations that transformers have that start putting these variables inside them, and this leads to the behavior of so-called few shot learning. So just let me talk about what are the few types of in context learning, and then we will talk about the perhaps the question little bit on how this happens in the model. A zero shot means absolutely have not shown anything to it and you still ask the question, like in this case translate to French, and then you give the word apple, right? That is just the zero shot. Model has not known this task of translation before, it's seeing it for the first time. It may be even be seeing French for the first time, right? Or any output that is relevant to French. A second thing could be like a more simpler one for the model would be what is called a one shot, right? A one shot would mean you provide one example and then the model understands that it is the French translation task. So you say apple to palm and then you ask banana. Suddenly when you can give more and more shots, you start increasing the model's mapping ability. So in this sort of few shot ICL or in context learning, people have come up with ways to understand this more mathematically. So early, let's say work in 2023 and so forth, they start looking at linear options, right? Let us say I want to have a linear regression function. So for simplicity, let's assume that y is 2x plus 3, okay? It's a simple linear function of x. So you have given one or two examples of x and 2x plus 3. Now we are giving a third example and the model has to learn that it is indeed the operation of 2 times the input plus value 3 added to it. It has to learn that with just 2 examples, right? So if you just want to solve a linear regression of this nature, what are the number of steps and parameters you want? Typically transformers require twice the number of examples, okay? This is the fundamental mathematical bound that they come up with. If I want to solve a linear regression with k degrees of freedom, in a linear regression solver you will need k examples, but in a transformer world in performing in context learning, they said that you need about 2k examples to get the same error bounds. Okay, so certainly you need more samples, although you have only in this case 2x plus 3 has only 2 parameters, which is ax plus b form, right? A and b are the 2 parameters. If you give 2 examples and tell me that it's a linear function that you are trying to solve, I might be able to find a and b with just 2 examples. But the model requires 4 examples because it has to store the internal variables, and certainly you are not teaching any loss reduction. And they also start looking at more than linear inputs. There are subsequent papers to this to say that maybe I don't want to do linear functions, I want to do polynomial functions, I want to do functions which are based on a regression tree, functions which are based on a neural network. Can a trained neural network be approximated internally in a transformer through in-context learning and so forth? For some level of such mapping functions, the in-context learning has shown value. People also start arguing, there is a thread of papers in this, I have not cited it here. They also say that this is not an inherent ability that happens once the model is trained. Okay, implicitly, even during the training exercise, this in-context behavior is seen over the training stack. Has been some literature around those. Okay, so but something that is very interesting, that you provide absolutely no way to change its weights and it still is able to learn a new task on the fly. Now we'll talk a little bit about the allowance of model weight learning, but in a small fashion. You want it in a parameter efficient fashion. You may not have significantly high number of task samples to train or adapt the models. You still want to do something very efficient with this, and one of the most popular techniques in this is called LoRA, or low rank adaptation. Again, I am going to simplify much of the math and the details in it to bring this out. So suppose, let us say we have some weight matrix, right? So think of it as any weight matrix that you had in your transformer model, be it the weights that associate with query, key or value, or in the feed forward layers. And now you want to say that I don't want to have so many number of dimensions to change. So then you say that, okay, I am going to allow change only in the form of some B times A matrix, where B and A are much lower in rank, right? So A is a R rank matrix, B is also another R rank matrix, and small d and capital D are much bigger. What you are then saying is the adapted or updated weight is of this form, where only B and A are learnable, right. So, the rest of the parameters are frozen. So, if I have W naught as frozen, B and A as learnable from the data, what does this allow us, right? As compared to if I let the entire W naught be learnable. If I let the whole matrix learnable, I have to deal with capital D cross small d parameters. If I let only A and B to be learned, then I am restricting myself to the number of parameters being R into capital D plus R into small d. If you see a simple example where D is capital D is 1024, 128 for small d, and you pick a small value of R, you already see that the savings in parameters that you are learning is about 93%, right? Only 7% of parameters are updated. But what happens internally is, with even a small rank constraint in your update, you can push the models to learn much more efficiently than, let's say, picking the weights, certain subset of the model to be learned, picking certain small portions of within transformer itself to be learned, etc. As compared to any of those choices, the rank constraint turned out to be the best candidate for a parameter efficient fine tuning structure. So, in a typical application, where are it done? Most cases you do this on the query and the value projection matrices. This is basically a very empirical result, even the paper alludes to it, that you do this on the query and the value matrices, you get the most parameter efficient fine tuning setting. So, another argument that came also from the paper is, it states this, right? When you want to relearn or take a model trained for a certain task and then learn it for a new task or skill, it doesn't require you to fundamentally relearn everything. You just are looking at shifts which are like in the form of a rank, a small rotation, a small change in the small number of dimensions or degrees of freedom that you allow, so that the shift is constrained in particular ways but still effective to move the model to the new task. Okay, extremely popular way of moving models to new tasks and settings. I will skip this Q&A for now because we have about 5 to 10 slides only. We will try to cover them and then I will open the floor for more questions. So, let us start looking at now how to pre-train, how to define tasks, right. So, everyone is aware why do we need to go beyond a supervised data setting, because it is difficult to collect, it is limited in availability, it is task specific, but of course, the value of a supervised data is very clear, right, like it is the most specific, most goal oriented form of learning. The unsupervised world is certainly the volume and the scale is high, but again you are extremely goal unaware, right. You don't have an alignment or an allegiance to a particular task or goal. You are just learning what the data distribution looks like. You are just learning what the domain of the data looks like without having any goal in mind. So, self-supervision in some way. The other thing that is largely different between an unsupervised and a supervised setting is, typically supervised learning is a categorical learning, meaning a classifier style learning, where you have a 1 to k mapping, right. You have to map it to certain buckets of k number, and in an unsupervised setting, what is this k and what is it that you want to map it to, they are all unclear. So, we want that categorical mapping, which certainly neural networks are very good at. We want to marry that with the abundance of data that unsupervised world provides, and turns out that self-supervision forms that nice sweet spot, right. Again, what does it do that is different from supervised or unsupervised. Let us start seeing that. So if you have an input data X and a labeled output Y, the mapping that a supervised setting would do is to take the X to the Y hat. If you have unlabeled data, then you can do some sort of a function learning. Maybe you apply some transformation and unlearn the transformation, remove some noise, encode the data in an auto encoding fashion and bring it back to the original data itself. All these are unsupervised learning frameworks, but they may not be largely categorical, and secondly, they don't have a particular task or goal in mind. They are broadly trying to maximize the probability or likelihood, in some cases minimize the reconstruction error and so forth, but it is a very loose goal of identifying the characteristics of the data. So in self-supervised, what you try to do is you derive auto labels. You say that data can itself be construed in different ways to somehow generate some automatic labels. Right? This auto label generation in this setting is called a pretext task. Right? So think of maybe clustering as one example. If I cluster the data, it automatically becomes some labels for you to map them to. Right? So this cluster indices become your data targets. This Z becomes your cluster indices. The data becomes your input, and now you can learn a function that maps the data to its cluster. Several ways in which you can construct this pretext data. Again, it is domain dependent, data volume dependent, and the model architecture dependency also exists. So if you look at the history of self-supervision, I would also say that it's about 7-8 years old, where people have started looking at different constructions of this pretext task. The key novelty has been how to do this pretext task. So we'll spend about a couple of slides on what this pretext task is and how to define it, and then extend that to the current era of modeling world. So just to remind everyone and bring everybody on the same page, what is a pretext task? A pretext task is something that generates a pseudo label, right? It's an auto label for the input data, and then you can convert this model training process into two subparts: an upstream model and a downstream task. So in an upstream model, you take every data point and create some sort of a pretext task and a pseudo label Z, and then learn this mapping from the data to the pretext task outputs, which are this Z hat. Once you have learned this to sufficient level of satisfaction, you say that some part of it is going to be repurposed. Some representations that come out of the pretext task are supremely useful. I can build on top of this a new set of layers that are now going to allow me to focus on a downstream task objective. Okay? This is the whole era of self-supervision and fine-tuning. Right? When we talk about LLMs and so forth, we'll talk about pre-training and fine-tuning and all, but this can be traced to this pretext task formation, this upstream downstream classification of how you define a pretext task, how to get the labels and learn a mapping, and then update the model. So you may ask, okay, now that a pretext task is something very vague, can we do bit more concrete definition of what are some pretext tasks, right? So again, this is a summary of many papers and taken from a survey work that has listed this. So simple things, for example, in an image setting, if I rotate an image, if I transform an image of a dog face, it's still a dog face, right? Of course, if you flip it vertically, you may start arguing, is it a dog or not? Maybe the answer is that you don't want to call it a dog, but any horizontal flips, 90-degree rotations of that nature, you can still call it a dog. So now you can ask the question, can I predict the transformation you did? Can I basically compare this and then predict the transformation? Since you did the transformation, You may have a fixed number of classes in which you did it. Maybe you did it for 45 degrees, 90 degrees, 135 degrees and so forth, and then you want to basically call that rotation axis as your class or category that you want to map it to, and you want to compare the two and say that these are offset by X amount of angle, right? That could be one transformation prediction task. Perhaps the most popular one, I will also talk about it a bit more in detail in the text era, is the masked prediction. You give partial inputs and you ask the model to do in the image world what is called in painting, right? You basically give this context and try to predict the rest. You give partial inputs and try to fill the rest of it, and this has shown to be a very valuable, vital task. Other examples include instance discrimination, meaning every instance you call it a class and you try to separate it from other examples in your training data by maximizing, minimizing some sort of a loss. And maybe a more relevant update of this is the contrast instance discrimination task, which is you take an image, rotate it, and then you call it this is the same, but take another random image in the data set and call it a different one. There you can now define two sets of tasks. One is to pull together image and its transformation and pull apart any other image that is available in the data set. Right? You don't know the class, you don't know the characteristic of the input, all you know that you apply transformation on one and any other random pick of an input data point has nothing related to your current input at consideration. So in the machine learning world, again, these are called triplet losses, where you can form an anchor, a positive, an anchor and a negative, and then you pull the positive pairs together, push the positive negative pairs apart. So that kind of a loss is well defined and studied and can also be applied for pre-training or this pretext task. We also mentioned a little bit about this clustering kind of task. You can surely take data and its transformations, generate some data clusters, and now apply some mapping. Last but not least, you can also combine many of these. You can do a clustering and a masking, right? You can mask parts of the image and cluster it, and now you can try to predict the cluster outputs of the masked regions, and they become even more powerful than by each one of these tasks in isolation. Right? So that is exactly the masked language modeling, which has become in the text world a very popular transformation, which is that you give randomly parts of the text and call it masked. So in this case, I picked the same example, like I am a student of machine learning. I randomly chose to mask student and off, and then we basically present it to the model as some noise in there. And now the model's job is to bring the region that is noise or mask back to meaningful words like student and off. Given the context of I am a and then machine learning, model has to now ground it to what could be the most plausible filling of those masked regions. Right? So BERT is the name of the paper. It's again 2019 work which popularized this to form transformers as core encoders. So the BERT is bidirectional encoder representations of transformers, and now once you learn this model, it becomes a very general purpose text representation model. You have not defined any task. Maybe I want to basically do it for sentiment analysis, maybe I want to do it for topic summarization, maybe I want to do it for understanding, let us say, the tone and tonality of the question, right? So many applications, maybe I want to understand the meaning of what is being said, right? Is it in the context of a educational setting, is in the context of, let us say, a virtual seminar setting and so forth, right? So lots of different ways in which the model can be repurposed once it is learned on this MLM task. It becomes a powerful encoder of text. You can now do the same, as I mentioned, to other modalities, right? And therefore you can create encoders of audio. In this case, you take windowed representations of audio, you can apply them, make them vectors of certain dimension, you can quantize them, and now you have a series of discrete indices, right? Now you can choose to say take certain portions and mask certain portions. If you want me to let's say draw this, we can also let us say that you have a portion that you want to mask out, and then you want to ask the model to predict the tokens or the discrete quantizer output that is indicative of the audio activity in that window, right? You can take the audio, convert it into vectors, certain vectors can get masked out, and then you can ask with the rest of the information, try to predict these token or quantizer outputs. If I can apply it to a continuous domain signal like an audio, I can certainly do that for images too, right? You can again take an image, make it into parts of this nature, what the vision transformer calls as patches, right? Every patch is now encoded into some quantized token world, and now your input image can be ordered in particular way. Maybe you want to call this as the first, this as the second, this as the third, and so forth. And now you have a sequence of patches coming in, the corresponding tokens being the quantizer outputs, and you can then start saying that okay, I want to mask this part of it, I want to mask this part of it, and given the rest of the context of the image, can you predict what are the tokens that represent this masked parts, right? So you are basically trying to infer that what is not given partially with the information of what is given. Again you are categorizing it, again you have like a fixed number of such tokens, so it is still a classification or a categorization task at the end of it. You are not trying to predict the exact pixel values, so it becomes a easier task for the model to learn it. And how much you mask out, what is the size of the patch, these are all people have engineered and played with it and come up with very good architectural solutions. So 2-3 more slides. So if you can do vision, if you can do audition, if you can do text, you can certainly do a lot more. You can take biomedical data, you can take finance data, you can take wearable data, and so on and so forth, right? So you can now look at the plethora of data and call it a union of different token subspaces, and every representation, every data can become a sequence of tokens, and now you can start modeling this union itself in a multimodal fashion, right? We'll talk a lot more about it in the next session on multimodal LLMs and other things, but that is where they are situated. So going to a little bit of what is going to come up, right, in terms of large models. So we talked about task of self-supervision, we talked about audio, visual and other modalities beyond text that can be crowdsourced but can be web mined, can become your input points without any labels, restrictions. So that covers the scale part. Now you can also push the models in terms of parameter sizes. Maybe I don't want 1 or 2 layers of transformers, I want 12, 24, 48 layers of transformers. You can then decide your pre-training and objective task, could be the MLM, could be the next token prediction, and certainly you have a monopoly also, a small number of players with high valued computational resources becoming the big players in the scale game, right? And finally you can take these models and take them to certain tasks using some forms of fine tuning. So we'll talk a little bit about pre-training and fine tuning in different ways and means to do this for large models. But fundamentally these are loading the parameters of the pre-train and then ask that to be the initialization for any subsequent training process. So let's just spend a little bit of historical context, how things have moved, and that sets the stage for the LLMs that become the topic for the next week's discussion. So encoder models were largely the first players in the field, right? They were bidirectional attention based, like the BERT, the Hubert that we discussed for speech, like the VIT we discussed for speech, and fundamentally if you ask me, their purpose is to create generic purpose representations of data. They are suitable for several downstream applications, and they are going to help you reduce the dependency of task specific labels. Right? Use them to encode it, be it text through BERT, be it audio through Hubert or other variants of models, be it images through variants of VIT and other relevant models. These become your powerful visual, audio or textual representations. Then the value addition through sequence to sequence models, primarily in a supervised setting. Suppose for some subdomains, let us say you have large volume of supervised data itself. Can I now bring that to fore in a transformer setting? And then came these models called encoder decoder models, where you can define a fundamental sequence to sequence loss on large scale. Say translation, you have different Wikipedia articles for the same topic, same comment with different translations. Can I mine all those Wikipedia articles and create a pairwise translation data point, train sequence to sequence models for it? Turns out that models of this nature, which are called T5 or MT5 and so forth for text, which are encoder decoder models, became very powerful translation models. For speech recognition, one of the still the most popular models is called Whisper. It can take speech to text, can train it on significant volumes of supervised sequence to sequence loss, and becomes very useful for those tasks. And more recently, right, as we start talking about it, the push and move is towards decoder only models. You use causal attention and an auto-regressive setting. What do we mean by auto-regressive setting? Every time you generate only one output, and once that is generated, it goes back into your queue to generate the next one. So every single step is a prediction of a next one that becomes the input to predict the subsequent one, and so forth. Again, they are trained with this next token prediction losses, allows free form generation. Of course, all of us are familiar with all these models that have become very popular in the modeling world, like your GPT, your Gemini, your Llama, your Mistral, Cloudy. There is a plethora of models like DeepSeek, Qwen. So there is a significant number of players also coming out with their own models. More recently, Indian models from Sarvam and so forth are also started to come in, which are free form generation models. They are trying to understand the next token prediction task to the certain modalities and then try to perform them for those languages or tasks or modalities. So just the last slide, right? So this has been, let us say, a little bit of this series or this particular session is a bit of a primer to build towards what has become more and more like a revolutionization of this kind of field. So transformers as a powerful model came in, self-supervision as a task came together with the transformers and then became the seed to the scalable models, which we call large language models, and that is basically the way the evolution has happened in the last decade that has pushed these model architectures with task and problem specification that has also shown efficiency, and then that has combined to the LLMs, which is going to be our subsequent topic of discussion. So thank you everyone for your patient listening of this video lecture series on transformer based models, the architecture, self-attention, and aspects related to pre-training, self-supervision, and decoder, encoder, decoder, as well as encoder only models. So continuing this journey in the next setting would be on large language models. This is going to take your transformer models to subsequent scale. In particular, we'll talk about pre-training tasks, multimodal large language model construction phenomenon. We'll talk about fine-tuning tasks through post-training, through reinforcement learning, and so forth. So this will be part of the subsequent lecture that is going to cover the LLM related topics. Thank you.